Hello, so here we are for the second talk of this conference, and it's a pleasure to introduce Professor Fiametta Battaglia from Universita Degli Studi di Firenze, and she'll be giving the second talk in the mini-course on non-rational Toric geometry, second part, Quasifolds, Foliations, Combinatorics, and one-parameter families. Fiametta, thank you for agreeing to speak.
So, okay, so thank you so much for the invitation. It's a great opportunity to speak in this conference, and I hope everyone hears me. So maybe I can start.
Perfect. Yes,
great.
Okay.
Okay, so this is the second talk of this mini course, and Elisa just gave the first one. And so I will carry on the same topics. So first of all, let me recall a little bit. Okay. So so in classical Toric geometry, we are able to associate to a rational fan or a rational polytope a Toric variety. And so it's been an open question for many years if this feature could be generalized to non-rational fans or non-rational polytopes. And we have just seen that Elisa first gave a solution to this open question in the late 90s. And I would like to stress that some key ideas in her paper and in her construction are fundamental elements for non-rational Toric geometry. So we see this picture here. We always have what I will call the convex geometric side of this picture. So we have convex object on one side, and we can associate to this to a convex object on this side a complex or symplectic space on the other side. Okay, so this picture has been generalized to the non-rational setting, and as we saw, the paper that has initiated this is by Elisa. And let me recall some key elements of her article. So on the convex geometric side, we have a polytope. So on this talk, I will speak about polytopes, even if in some context I could consider fans, but I will stick to polytopes for the whole talk. So because otherwise I think it's too confusing. And I will switch to fans in the next one. So let's consider a convex polytope. So the convex object that we need, our starting convex datum, is a triple, as we have seen in Elisa's talk, that is given by the polytope, the vectors, the normals that Elisa just explained, and a quasi-lattice Q. So the vectors are normal vectors to the facets of the polytope, and they lie in Q. So I'd like to stress that this triple, this starting convex object, we do have the same datum in rational in classical toric geometry, because so whenever we say, let's consider a rational polytope, when we say rational polytope, we mean that together with the polytope, we are considering a lattice. We have a lattice, and also we have a canonical choice of normals that are the primitive ones. So even in classical toric geometry, we have this starting triple that is polytope, lattice, and primitive vectors. So this is a very, very natural generalization of the rational setting into a non-rational setting, where, as Elisa explained, the lattice is replaced by the quasi-lattice. So having this starting datum, as we saw in the previous talk, when in the triple we have a simple polytope, a quasi-lattice, and the normals in the quasi-lattice, then we can associate to this triple a symplectic toric quasifold that was, this construction was given by Elisa in 1999. And we can also construct the complex counterpart of this toric quasifold as a complex quotient. And this was, and I would like to give some more details on this complex toric quasifold. So, okay. So in order to construct this space, we generalize a construction that is a combination of the generalized Delzan construction that was that we had from the symplectic case in Elisa's paper, and a construction given by Oden, where she constructed complex toric manifold as complex quotients. So we have our initial triple, a simple polytope of dimension n, h vectors. Here h is the number of facets that belong to a quasi-lattice Q. This polytope, simple polytope, is quasi-rational with respect to the quasi-lattice Q. And this was also explained by Elisa in her talk. So correspondingly to this triple, we have a complex quotient that is constructed in this way. We have an open subset of CH, and this subset is only depends on the combinatorics of the polytope. And then we have a subgroup NC of the torus C star to the H, which is possibly non-closed. Let me remark then this torus, as in the, you know, in the, I mean, this is NC, this torus is connected if and only if the span of the normals is Q. This is not always the case. And the topology that we consider on this space is the topology of the orbit space, is the quotient topology. And I would also like to remark that the complex structure, this complex quotient, only depends on the normal fan to the polytope. I mean, the polytope defines a symplectic structure, so a further structure. But as far as the complex structure is concerned, we just that depends only on the normal fan to the polytope, as in the rational case. Okay, so we have this quotient, and I would like to to observe that this complex toric quasifold shares many features with the non-rational, with a toric manifold. So let's consider first X delta n, a smooth, a toric manifold. So there are, what can we say? We know that the toric manifold is covered by homogeneous charts that are indexed by the polytope vertices. And each of these charts can be identified with Cn. And also the toric manifold is the disjoint union of orbits of the torus C star to the n. We have a dense open orbit that corresponds to the interior of the polytope, and we have other smaller orbits that corresponds to the polytope faces. Each orbit corresponds to a polytope face. This set of orbits is indexed by the polytope faces. Let me tell you here that delta is a simple polytope, so it is the moment polytope, and that's why the dimension of the orbit of the torus is the dimension of the face. Okay. And also, as a last remark, the combinatorics of the polytope is linked to the topology of the manifold. So we would like to see that in the non-rational setting, we have all these, we have features that are analog to these ones, and also the link in combinatorics carry on the non-rational setting. So let's see. So, so we have that if X and delta is now a complex toric quasifold, it is the union of homogeneous charts. It is covered by homogeneous charts, and each of these charts is can be identified with Cn, but here we have to mod up by a countable subgroup of S1 to the n. So this is, one can see very clearly the quasifold structure of the space here. And also our complex toric quasifold is a disjoint union of orbits of the quasitorus, of the complex quasitorus here. I'm not spending much time in defining these objects because Elisa's already defined them in her talk. She already went through what is quasilattice, quasitorus, and so on. Because these are all objects that she introduced. X and delta is this disjoint union of orbits of the complex quasitorus. And again, we have a dense open orbit that corresponds to the quasitorus, and to this and then there are the smaller orbits that are indexed by the faces. So the big dense orbit is C star to the n mod up by, again, a countable group, and the smaller orbits are C star to the p mod up by, again, a countable group. So really we have the same kind of say decomposition of our complex toric quasifold. It's we can see it really reflects the structure of what we have in the rational case. Okay, and so what is the relation with the symplectic quotient? We have already seen that they can be identified. So how does this work? How does this identification work? We have the level set of the moment mapping that allows us to construct the symplectic toric quasifold. This level set is contained in the open subset U delta, so there is a natural inclusion map. And this map, when we pass to the quotient, we descend to the quotient. This is, in fact, we prove that this is a diffeomorphism, and the symplectic structure on one side and the complex structure on the other side are compatible. And this is this picture that we have here is also very classical. So it's in many different settings we can see that the symplectic reduction is isomorphic to the corresponding complex quotient. And so we have the same situation here. And why this, we have this, why we have this identification, what is it that makes it working? So let me just say in some more detail that the group NC can be written as a product of N, the group that we have seen in Elisa's talk, by exp IN, with little n is the algebra of N. And we have that the exp IN orbits are closed in U delta, and U delta is actually the saturation of the level set by the x pi n orbits. They are all closed, and this is why when we consider the complex quotient, there is nothing new from the viewpoint of the topology of the quotient space with respect to what we had in the symplectic quotient. This is because these orbits are closed. And then we prove that each NC orbit in U delta intersects the level set in exactly n orbit. So that's what makes the mapping chi from one quotient to the other bijective. Okay, so this is, because of this, the two quotients can be identified. And what I would like to address now is the relation with the combinatorics of the polytope. So this is a very classical, interplay in toric geometry between combinatorics of the polytope or the fan, depends on your viewpoint, and the topology of the toric variety. And this is has produced important results. So it is a natural question to see if this carries on. So we want to see if there's a relation between combinatorics of delta and our complex toric quasifold. So, oh, sorry, I am looking at the time. Okay. So in what we know, and because we look at what happens on the rational, in the rational setting, and we want to see if what of the phenomena that we have on the rational setting are also true and hold in the non-rational case. So we know that in toric geometry we have a very precise relation between the Betti numbers of the toric manifold, because we are considering here simple polytopes, and the H vector of the polytope. So let me just recall, when we have an n-dimensional polytope, there is a natural vector that is associated to the polytope, that is the so-called F vector. The F vector counts the faces of given dimension. So F0 are the vertices, F1 the edges, and so on. And from the F vector we can construct what what is called the H vector. It is another vector with natural coefficients, natural numbers as coefficients. And this is completely determined by and determines the F vector. So we can get one from another. And this only happens, as we will see, in the simple or simplicial case. Okay, so classical result for toric manifolds is that the Betti numbers of the toric manifold are the odd Betti numbers are 0, and the even Betti numbers are given by the H vector of the polytope. And in a paper in 2011, I tried to generalize. I wanted to see if this fact was true also for complex toric quasifolds. And so actually, if we take a simple polytope, one can see that we can define the de Rham cohomology of the corresponding complex quasifold. When I say simple polytope here, I actually mean a triple. So we have a polytope, normals, and quasi-lattice. And we have, otherwise, we cannot speak about corresponding quasifolds. So I put delta, the polytope delta, as a short notation, but we have always to think of as the starting datum as a triple. So for any simple polytope, we can define the de Rham cohomology of the complex corresponding complex quasifolds, and we prove that the odd Betti numbers are 0, and the even Betti numbers are given by the H vector. So we again have this property. And so, well, I don't know if I want to go through this. So anyway, the key points for this result are, first of all, that there is this there is this open covering of X delta, very explicit, and you know, a very nice open covering, and the charts of all of this kind. And also we use a lemma that is very useful in this situation, and which is the following. If we have a compact connected group that acts smoothly on a manifold M, and we consider any subgroup of this compact connected group, then if we study the cohomology of invariant forms, we have that the cohomology of the manifold and the cohomology of T invariant forms are the same, and the cohomology of S invariant forms gets squeezed in between and is actually equal. We have equalities here. So with these two, you know, facts, we are able to prove what I said about the Betti numbers being given by the H vector. So we prove that there is, again, in this non-rational setting, this relation between Betti numbers and the H vector of the polytope. So let me now go on a little bit with combinatorics. I written here combinatorics of convex polytopes 1 because I want to say something about combinatorics also in my second talk. So let me recall here that a famous, very famous theorem, the so-called G theorem, gives a complete characterization of the H vector of a simple polytope. Okay, so and the proof of the necessity part. So if you have an H vector of a polytope, then this vector must satisfy certain conditions. So the proof of this part was given by Stanley in a famous paper in, I think, 81, if I remember well. So how does the proof work? So the first thing that one has to do is to reduce the problem to rational polytopes. So why are we able to do this? Because if we consider a non-rational simple polytope, we know that this can be always perturbed into a rational one of the same combinatorial type. So as far as we are interested in the combinatorics of the polytopes, we can just look at the rational ones, and this is what Stanley does. And then he proves that the H vector of a simple rational polytope satisfies certain conditions. He proves this by using Hodge theory on the corresponding toric variety. Okay, so this is the argument of this proof. And what happens when the polytopes are non-simple? So the G theorem was proved in this way for simple polytopes. When the polytope are non-simple, the situation is a bit more complicated because there are non-simple polytopes that are non-rational. Sorry, this is not very clear from what I wrote. There are non-rational, non-simple polytopes that are not combinatorially equivalent to rational ones. So this means that the combinatorics of non-rational, non-simple polytopes cannot be deduced from the combinatorics of rational ones in a non-simple case. Okay, so the G theorem was extended to the non-simple case, but for non-rational polytopes, the proof is purely combinatorial. Okay, so this is for rational ones, one can again consider the interplay between polytope and toric varieties. In the non-rational case, there were not toric varieties corresponding to non-rational polytopes. So the proof that was given by Calle-Caro in 2001 was purely combinatorial, and this is still the state of the art. And let me also remind that the characterization of the F vector is an open problem in the non-simple case because we cannot recover the F vector from the H vector in the non-simple case. So the non-simple case is really more involved. So there are some questions that arise from this discussion. So the first one is that we can ask ourselves if in the proof we can give a proof of the G theorem that avoids the reduction to the rational case. So if we can give a proof that unifies the rational and non-rational case by considering a toric space that by considering a certain toric space. So we would like to see. This is, I think, a very natural question, and I will address this question in the next talk. And another, I think, quite natural problem that was raised by what I said, what I just said, is that are there complex or symplectic spaces that correspond to non-rational, non-simple polytopes? So up to now, we have talked about simple polytopes, but we have seen that actually non-simple polytopes are very interesting, and so we would like to know if we can extend these constructions that we have seen to non-simple polytopes, and we would like to know what are the spaces that we get. So let me just say a few generalities about polytopes. I often forget to say convex, but all the polytopes that we are considering are actually convex. So a convex polytope is the disjoint union of its open faces. Okay, I think this is pretty clear. And let's see. We have seen in the simple case that the complex toric quasifold was modeled on the polytope. So this is going to be still the case in the non-simple case. So we want to see what is the we want to look to our model, the polytope. So if we take a polytope delta, and we take an open face F in this polytope of dimension P. So this polytope in a neighborhood of this open face can be written as a product of the face itself by a cone over a polytope that we call delta F of smaller dimension. This polytope delta F is not uniquely defined, but the combinatorial type of this polytope certainly is. Okay, so we have this local, say local structure of the polytope, and then we say that F is a regular face if this polytope delta F, that is which we will call the link of the face F, is a simplex. So a face F is regular if delta F is a simplex, and it is singular otherwise. So when we have a simple polytope, all of its vertices are regular, and this implies that all of its faces are regular, and otherwise we have a non-simple polytope. So again, what we can do is further generalize the Delzan construction. As Elisa said, we just follow the Delzan construction step by step until the very end, and we get a quotient of the same kind. So we have the level set of the moment mapping and this group N. But we have then to see what is the object that we end up with. So in this case, we have the group N as Elisa found in the simple case is a possibly non-closed subgroup of S1 to the H. Let me recall, is the number of facets of the polytope. But the new thing in the non-simple case, the new phenomenon, is that the level set is singular. It is not a smooth manifold any longer. It's singular, and this happens also in a non-rational case. And so let me say that this construction, this extension of the Delzan construction to the non-simple case was new at the time, and so I think it's also interesting. It was, and it is also interesting to look at the rational case in this for non-simple polytopes. I mean, for any kind of polytopes, but in particular for non-simple ones in this, say, singular situation. So examples, as we already, Elisa already mentioned, are the octahedron, the icosahedron that were treated in this joint paper in 2017. And let's see what we get. We get a stratified space by symplectic quasifolds, and the stratification is modeled on the polytope. I'm going to show this in more details after I also talked about the complex case, because even in this case, I mean, still the two quotients, the symplectic non-simple space and toric space and the complex non-simple toric space can be identified. So the stratification is the same. And so I will talk about it just later on. So we have this symplectic space stratified by symplectic quasifolds. And in the rational case, let me just devote 1 minute to this. The regular stratum is either an orbifold or a smooth manifold, and the singular strata are smooth. This is what happens in general. And the symplectic quotient, the symplectic reduction here, in this case, in the rational case, is a special case of the singular symplectic reduction that was introduced by Shamar and Lerman in 1991. So the singular symplectic reductions when we consider a value that is non-regular for the moment mapping. Okay, and let me also say that when on this symplectic space, we have a map that has the role of the moment mapping and whose image gives the polytope back. So we really have, again, not only the space, but also the moment mapping and the quasi-torus action. Okay, so we go on with the complex non-simple case. And what we do here, we still applying the construction that we made for the simple complex case. We have the same elements. We have an open subset of C to the H that only depends on the combinatorics of the polytope. And we have the group NC that we can still write as a product of n by exp in with n the Lie algebra of n. But in this case, we cannot take the orbit space as in the as it happens in the rational case. That for the rational case, I mean, an inspiring work was the paper by Cox in which he constructs toric varieties, simple or non-simple, so smooth or singular, as complex quotients. So, and this phenomenon also happens in the rational case. So what is new here? So we still have that if Q is not a lattice, N is non-closed, and as we have seen in in general in this kind of construction. So what I mean, why I wrote again this about the group N being non-closed, because we have two kinds of singularities here. One is due to non-rationality, and the group that is responsible for the singularities due to non-rationality is N, this N here. By complexifying, as I said, we don't add anything. So N being non-closed is a consequence of the non-rationality, while the other phenomenon that is for this case when delta is non-simple, and this is specific for this case, is that there are non-closed exp in orbits, non-closed in U delta. Okay, and this is responsible for the quotient being a stratification. Okay, So we have two kinds of singularity, quasifold structures and stratification. Quasifolds come from non-rationality, stratification comes from non-simpleness of the polytope. So how to make sense of this quotient? So first what we have to do, we characterize those x, I, and orbits that are closed. So between all the orbits, we characterize those that are closed. And also we prove that if we have an unclosed orbit in U delta, its closure contains one and only one closed orbit. With these elements, we are able to give a notion of categorical quotient in this setting that allows us to construct X delta, the corresponding space to a non-simple, non-rational polytope, as a quotient, as a complex quotient in this sense. So we don't take the orbit space, but we quotient by this equivalence relation. That mainly, so essentially, when is it the 2 points are equivalent if modulo the n action, the closure of their x, pi, and orbits intersect. And this is also what happens in the rational case. So we get this quotient. So we start again with these fundamental elements, this triple, polytope, normals, and quasi-lattice. We get a corresponding quotient, and we prove that this is a complex stratification by quasifolds. In particular, the regular stratum is an n-dimensional complex quasifold, where n is the dimension of the polytope. And this regular stratum is given by the union of the regular quasi-torus orbits, and this include the dense open orbit that corresponds to the interior of delta. So even in this case, this quotient is the disjoint union of orbits of the quasi-torus. The regular orbits, the one that corresponds to regular faces, we put them together, and this gives us the regular stratum. And then we have the singular strata that are indexed by the regular faces of the polytope. Okay, and what is the structure of this singular strata? Each of these strata is a copy of C star to the P mod a countable group that I call gamma F. Again, a countable group. So this gives the quasifold structure of strata. Okay, so the stratification, the structure of the stratification, so we have to prove that up to now we have said that we have a decomposition of our space into pieces, a regular piece and singular pieces that are indexed by the polytope faces. So the structure of the stratification is, we can read the structure of the stratification on the polytope first, as we already saw. So we have a neighborhood of an open singular p-dimensional face is a product of this face F cross a cone over delta F, where delta F is an n minus p minus 1 dimensional polytope that is not a simplex because F is a singular face. So we prove that if we take a singular face and we consider the corresponding stratum F, we take a neighborhood we can take a neighborhood of this stratum and prove that it is homeomorphic to a product of this kind. So we have C star to the P is the dimension of the face, cross a complex cone over a complex space, again stratified by quasifold, and this X delta F corresponds to the link delta F. And I must stress the fact here that when we construct this delta F, we get not only a polytope, but also we construct delta F by a process of by making a projection. And we get not only a polytope, but also a set of normals and a quasi-lattice. So we have a well-defined corresponding complex space that we call the complex link. And then we have to quotient by gamma F that acts not only on C star to the P, but also to this complex cone over X delta F. So we have it is not a true product, but it is a twisted product. And this gives us the stratified structure of our space. And also a very strong property is that, of course, the neighborhood of a stratum is itself a stratified space. This product here is a stratified space. The stratification is induced by that of X delta F. And so we have this homeomorphism between these two stratified spaces. And we prove that the restriction to strata of this homeomorphism is a biholomorphism. So it keeps the complex, the holomorphic structure. Okay, so this is for the stratified structure. And I want just to remark, it's this very, very simple remark, but I think it's quite nice to observe the following. Why? I said in the rational case, the regular stratum is smooth or an orbifold, the singular strata are smooth. So why we jump from smooth strata to strata that have the structure of a quasifold when we consider the non-rational case? Because strata, remember, are C stars, say C star to the P mod the action of a countable subgroup of S1 to the P. So we have this just to make an example, I just take the punctured unit disk. This pink point is the origin. So when we consider the quotient by a finite group, since we don't have the origin here, we get something that is smooth. But if this group is one of our countable groups, then the quotient is a quasifold, and that explains why the strata in the rational case are all smooth. And let me finish by the statement of the theorem that identifies the symplectic and complex quotients in the non-simple case. So we have a starting triple. We construct the corresponding symplectic space stratified by symplectic quasifolds, the corresponding complex space stratified by complex quasifolds, and these two stratified spaces can be identified by a map that respects the stratification, and the symplectic and complex structures are compatible, meaning that the map that identify the two spaces when restricted to the strata really gives a diffeomorphism in which the symplectic and complex structures are compatible. And so I think I can stop here. Thank you very much for your attention. So,
thank you so much for such a nice talk. From the audience, any questions for Professor Battaglia? I have a little question. When you stated about the G theorem,
yes.
you mentioned that there are cases that are not established or something. I lost my track a little bit there. Could you repeat a little bit that story?
Let me see. So you tell me exactly the point. Is that the slide? So the only thing that I said is still open is, I mean, here in this slide, there are actually a couple of things. The third point is that the F vector, a full characterization of the F vector for the non-simple case is an open question. So we don't know, I mean, in the simple case, we know that the F vector, a vector is an F vector of a polytope if and only if certain conditions are satisfied. We don't have the same kind of result for the non-simple case, and also
not even conjecture. There is not even a reasonable conjecture.
Well, I mean, I know it's an open problem. I cannot say
there's not a reasonable conjecture even. I mean, Gunther Ziegler has talked about this for a long time. Even understanding in dimension 4 would be a great dream of his. There are unusual lacunae in the space of F vectors. People don't know the linear or the nonlinear inequalities. It's kind of the Wild West.
Thank you. And also the other, I think, unknown and open is not really an open problem, but there is a proof for non-rational polytopes that is purely combinatorial, but we don't know of any proof that is based on the topology of corresponding toric spaces. I mean,
there is a proof though by Paul Bressler.
I think it's sorry.
If you believe that derived spaces are spaces, then it would fit the mark. But it is a bit of a stretch to call it the topology of the spaces. But I agree. Nevertheless, I think Paul Bressler's proof is very conceptual.
Okay, but does he prove it combinatorially, or he uses?
No, not at all.
So, what kind of spaces does he uses for his proof? I'm asking
derived category. He used this kind of derived geometry, derived spaces.
I see. I see. Thank you.
If I remember, the key to the G theorem was proving like a version of the Leschetz theorem, and Calle found a way to do this when it's combinatorial. So that's actually an interesting question in your case when you have some form of homology theory. Do you have something like a Leschetz theorem there? That's
yes, maybe that is what I meant. But for the non-simple cases, I mean, all this part is still. I mean, we just have the construction of these spaces, but we don't have, as you said, an homology or that we can relate to the polytope combinatorics. So it's like, I mean, in the simple case, we have Betti numbers and H vectors that are in relation. But here we just have the spaces, so it's hard to. We cannot speak of an Lefschetz in this case because we don't have all the necessary elements.
Any Any other questions from the audience?
Not yet, at least.
Well, thank you very much for such an. But this talk does continue tomorrow, right?
On Wednesday.
Wednesday. So this is only the second part of 3. So
Yes.
keep tuned for the third part, coming attractions. Thank you very much again.